Hello everyone, welcome to Chapter 4, Applications of Derivatives, and our focus here will be linearization and differentials. Let's focus on linearization. Can you see the word line in linearization? That's your big hint there. We're going to use the idea of lines here. And why do we need them? Well, this is basically a technique that is used to approximate complicated functions. So we're going to use the idea of lines to do this. So to illustrate this, let me give you an example. Let's take y equals x squared. You know, it's a parabola passing through the origin. And let's say we're focusing on x equals 1. Okay. So at x equals 1 on the curve, if you were to find the slope of the curve at that point, that would become your derivative at that point, right? But you also know that to use this linearization technique, you can we can prove or show that there will be a tangent line that passes through this x equals 1 that touches the curve at 1. And if you took the derivative of this, you know it's 2x, right? So you know that the equation of the tangent line actually is 2x minus 1. So if you use the slope, okay, slope of the curve at x equals 1, you know the derivative, let me show here, y prime is 2x, and when x equals 1, that will be 2 times 1, which is 2. So you have the slope, and then the point, when x equals 1, it implies y is equal to 1 squared, which is also 1. So 1 comma 1 will be your point. So if you use the point and the slope to get your point slope form, that gives you the equation of the tangent line. TGT is tangent line. Okay. And this is how it looks. So the red graph is your parabola, and the blue one is your tangent line. So let's get closer. That's a tangent line that passes through the point 1 comma 1. Yeah, because that was our focus. So we were focusing on x equals 1. The corresponding y coordinate is also 1. Therefore, it's 1 comma 1. And that's the point that's common to both the red graph and the blue line. Now, the technique of linearization says if we get closer and closer and closer, we zoom really closer, you look at the neighborhood of 1 comma 1. In fact, you cannot differentiate between the red and the blue. It seems like the blue overtook it. So your curve, which is a parabola in this case, appears like a line at the point of interest when we zoom in closer. In fact, you can see the red and the blue separate a little earlier or a little later, but at 1 and around 1, it appears that it's going to be coinciding with the line itself. In fact, if you go really close, then you begin to see that as if it's stretching even more. But then if you come out, even at this zoomed out level, you can see that they seem to coincide pretty closely there. Yeah? All right, so that was the idea of linearization. And so now I'm going to come back and write the definition. So our definition for linearization says, if f is differentiable at x equals a, then the approximating function L of x equals f of a plus f prime of a times x minus a. That expression is the linearization of f at a. So we're saying the approximation was as if f of x, the function, whatever the complicated function, that was approximately equal to that line L of x, the linear function that we found at that point. Now, remember again, this is linearization of f at a. It's not for the entire function because you can't just approximate a curve into a line. This is true only at that point of interest because that's where they coincide with the tangent line, and therefore we're using the idea, the technique here. And we also say that L is the standard linear approximation of f at a, and x equals a is the center of the approximation. We saw that, right? Because we saw a little above and a little below in the neighborhood of x equals 1, we got the line and the curve to coincide completely. And so we can see that it was kind of the center where this happened. I think we'll better understand with an example, so let's go for it. So a question reads, find the linearization of L of x, of f of x, at x equals a for this given function f of x equals x cubed minus 2x plus 3, and a is 2. So let's go back to the definition quickly to see what this means. Okay, f must be differentiable at a. If that is the case, then the approximating function, this L of x, for this f of x will be around that a, which is 2. So what we're saying is now f of x we know is a cubic function. It's going to be like a chair shaped, right? It's going to have 2 turns. So it's a parabola, and sorry, it's a polynomial, and therefore it is going to be differentiable at every point. And therefore we know that it's going to be differentiable at 2. Now we're saying what happens, or how could you approximate this with a linearization technique? In other words, can you come up with a line, with an equation of a line at that point so that this f of x, which is a polynomial, can be approximated to that? So to kind of illustrate the idea, I have the graph for you here. So this red one is the is our polynomial of degree 3, right? X cubed minus 2x plus 3, that's what we have. And our focus is at 2, so let me go a little closer. So at 2, we have the corresponding coordinate here to be 7, okay? So at 2, if you draw the tangent line, we know that the blue line is the tangent line, and the tangent line passes through that curve at 2, at x equals 2. The corresponding point is 7. So let's keep that handy. Now, if we were to find the equation of the tangent line at 2, right, that would give us an approximation for that curve, for the red curve at that point 2. So that is what we're trying to find here. So let's say using linearization formula, the formula says this new L of x, the tangent line, will be f of a plus f prime of a times x minus a. This is nothing but your slope point form that is rearranged. So we are not writing anything new, brand new here. Okay. So we have a here is 2, right? So we're trying to find f of 2 plus f prime of 2 times x minus 2. So if we can find f of 2 and f prime of 2, then we just plug that in and we get our L of x. This is basically your slope-intercept form, because when you finally write it, it'll appear in that form. But what you have here is a rearrangement of slope point form. All right, so I have f of 2. So I go back to the function and I plug in wherever x occurs, I replace it by 2. So if you did all that, that gives us 7. We saw that on the graph, right? 2, 7, we saw that. But if you computed it, you're going to get the same thing. So we got that. We need to find f prime of 2. But for that, we need to find f prime of x. Let's take the derivative of this. X cubed is 3x squared minus 2 plus 0. So let me write that just for emphasis. So basically, it's 3x squared minus 2. Now I can find f prime of 2. In the place of x, I plug in 2. And that gives us 10. Compute this, we get 10. 12 minus 2. All right, so we've got f of 2 and f prime of 2. I come back to this L of x. F of 2 is 7 plus f prime of 2 is 10 times x minus 2. Now we just need to simplify this. Minus 20. 10x, 7 minus 20 is, minus 13. So your L of x, the approximation of this cubic function at 2 comes out to be this line, 10x minus 13. In fact, that's what I had graphed here. Okay. So that will be, let me see. I don't think you can see the complete equation that I've written to get this graph, but you can see that that's what has happened, that we got the equation of a tangent line at x equals 2 for this approximation. So we'll do another similar problem where our f of x is given to be x plus 1 over x, and we need to find this around a equals 1. So we have a equals 1, and we have a function that is complicated in the sense that it's rational, right? So if we have this, we know that we need to find f prime of x. So that's going to be 1 plus, well, just before that, let me just rewrite this f of x as x plus x power negative 1. Okay, that way you can do the derivative easily. 1 over x is x power negative 1. So f prime of x will be 1 plus negative 1 times x power negative 1 minus 1. 1 minus x power negative j, which is the same as 1 minus 1 over x squared. We want to rewrite this in the positive exponent form. So we got f of x and f prime of x. Now we need to find them at 1. So what is f of 1? So 1 plus 1 over 1, which is 2. And f prime of 1 will be 1 minus 1 over 1 squared, which is 0. And so if I went back to the L of x formula, which was L of x equals f of 1 in this case, plus f prime of 1 times x minus 1. F of 1 is 2 plus f prime was 0 times x minus y. It was 2. So the approximation here is that it's going to be a horizontal line. Right? L of x equals 2 is a horizontal line that passes through the curve at x equals 1. So that is our linear approximation or linearization. Do another one. Maybe we'll try a trig function. So this is our function given to us, tan x. And the interest is at pi. What happens when it's at pi? And so to find the linearization for this, what is the this is definitely a curve, right? We know that. It's a trigonometric function. You know how a tangent line looks, right? It looks like this with the asymptotes and all that. So we're going to find an approximation for this, a tangent line for this at that point, x equals pi. We call it a equals pi just for the sake of the formula, right? But it's where x equals a, which is pi. So I'd like to find f prime of x. So derivative of tan is secant squared x. So I got f of x and f prime of x. Now I have to go ahead and evaluate it at pi. So tan pi will be 0 because it's sine pi over cosine pi. It shows 0 over 1, 0. Practically over negative. And f prime of pi will be secant squared pi. So secant squared is 1 over cosine squared pi, isn't it? And cosine pi is negative 1, so square that. 1 over negative 1 squared, or comes back as positive 1. And then now we can use the linearization. L of x is f of a, in this case a is pi, so f of pi plus f prime of pi times x minus pi. So f of pi is 0, f prime was 1 times x minus pi. So all this comes down to x minus pi. We found the linearization to be x minus pi. In our next problem, f of x is given to be 2x squared plus 3x minus 3, and a is negative 0.9. Okay. Now notice that the whole idea of approximation is to make whatever is complicated simpler. So now we have a equals negative 0.9, and this kind of pushes us to use the calculator to compute this. But what we can do here is we can approximate, because it's all about approximation. Therefore, it doesn't hurt us to approximate this a to a number that's much easier to handle. So let me, before doing that, let me just get the derivative here. F prime of a will be 4x, 2 times 2x, right? So 4x plus 3. And we're saying we need to find f of a. F of a is f of negative 0.9, but let's make it, I want to use the approximation symbol. We're going to approximate it to f of negative 1. We'd like to choose an integer, basically, to help with the computation. So I'll just say we choose an integer close to a. And we're allowed to do this since it's an approximation. You can't do that with exact values, right? You want the exact answer. So here we're using approximation, therefore f of negative 1 will be 2 times x squared plus 3 times x minus 3. And in the place of x, you plug in negative 1. Again, be very careful with your sign. Negative 1, the whole squared. Okay, that comes back as positive 1, but 3 times negative 1 will be a negative 3, so watch out for that. Those things combine to give us negative 4. Then we have f prime of negative 1, so I come back to f prime of x, and then 4 times negative 1 plus 3. That comes out to be negative 1. And so this is so much easier to find the linearization. So f of negative 1 x minus a negative 1. Double minus there. That's negative 4 plus a negative 1 times x plus 1, because I combine the minuses. And for f of negative 1, the answer came back as negative 1. Putting them all together. That'd be minus x minus 5. So L of x is minus x minus 4. That's what we do with linearization. Now let's move on to differentials. Now this dx and dy that we've been using, these are called differentials. And what's really neat when we see them as differentials is that they behave like independent variables. What does that mean? That just means that this dy over dx would be like a ratio. Okay. If they behave like independent variables, this would be a ratio. That means you can move the dy and the dx around. Let me show that to you here. Dy over dx is our f prime of x, right? We understand that. It's these two notations are coming together, the prime notation and the d notation. Because they behave like ratio, they would behave like independent variables, I can just multiply both sides by dx, and it appears like dy is f prime of x times dx. Okay, so what we're saying is like what did not seem separable in the beginning because it made sense like how fast is y changing with respect to x. When we kept it as a slope, we only could keep it as dy over dx to explain this process. But now when we see them as differentials, we are able to see them as dy and dx, two independent variables. Therefore, we could separate them out so that we can solve for dy not just dy over dx like we did in implicit differentiation. Here we're going to do dy, which can be written as f prime of x times dx. So I'll just give you a basic example here. So if they said find dy, and they gave you y as x power 5 plus 37x, what would we do? Well, we're saying previously, I'll just write the y one more time. Previously, we would just do dy over dx. So just do that. Take the derivative. That's going to be 5 times x power 4 plus 37, right? When they say find dy, we only want the dy. So you're going to multiply the whole of right-hand side by this dx. So put that in parentheses because the entire thing is getting multiplied by this. There's a reason why we do this. We will need this when we get to integration. So for that, we're building up this idea. But what is the purpose of this? What is the application? Because in chapter 4, we're talking about application. How do we apply this? We apply this when it comes to estimating with differentials. So I'll write that part here. Estimating using this idea of differentials. So if I had a small change to the a value, okay, a is a particular x value, okay, x equals a. So if that a is slightly changed by a small quantity dx, we're saying because of the way they behave, this will be like f of a, the function at that point a, plus the differential dy at x equals a. A small distance added to the a, if you were to find the function of that, that would be an estimation like this. Okay, so we're saying this delta x, the change in x, is a small change in x as a differential. You can see this actually with an example. So let's go ahead right into the example. If we said estimate 7.97 power 1 over 3. Okay. Now we have 7.97. We can't do this without a calculator. We're trying to find the cube root, because it's power 1 over 3 of 7.97. So is there a way to write this information using differentials and approximating the answer? Now what we can see is if I were to approximate this, the 7.97 would approximate to an 8. Cube root of 8 is 2, so we get that. But what we're trying to do here with differentials is we're able to go further and find the approximation much closer. So we're not saying, we're not running to the next whole number to give that information, but we are going to use something similar to get a more closer estimation. So let's first approach this by writing the y as a cubic function because we need the f of x, right? So let's do that. Let's write the given information as a cube root function. So we have this 7.97, which is the problematic part, right? So we're going to say let y equal x power 1 over 3. So I'm calling this a function, okay? And we're trying to basically find the function, I can also write it as f of x, as x power 1 over 3. So this x is what is problematic, and we're going to use differentials there. Right? But just before that, let's take the derivative of this, or find the differential of this. dy will be, in fact, I can show it to you, dy over dx first. It's 1 over 3 x power 1 over 3 minus 1, isn't it? So dy over dx is 1 over 3 x power negative 2/3. And we can bring that down. So dy over dx is 1 over 3 x power 2 over 3. Okay. Now we need to write it as a differential. So dy is 1 over 3 x power 2 over 3 times dx. So you don't have to put the dot there, but just want to show you that it's times dx. The whole idea is we have this information, so I'm trying to get the dy, and therefore I take the derivative of this function that I rewrote the original question as. So we are going to approximate that decimal information, 7.97 to 8. And for us to approximate it, to round it or bump it up to 8, we had to add a 0.03, right? So I'll say by adding 0.03. So what we're saying is, well, this a plus dx will be that x. And what is a? A is something we want to keep it convenient. So we want the a to be 8, right? Again, come back to the estimation formula, because we want to find f of 8. So if a is a nice number, it's an integer, it helps us even with the dy, because we need to evaluate dy at that x equals a. So we want that to be a convenient number. So a plus dx. So if I'm choosing my a to be 8, so I want this 8 plus dx to be the value that we chose, right? So for that, I want to come back here. Remember, this 7.97 is what I wrote as x, isn't it? So I rewrote that as x so that I'll be able to take the derivative, because if I didn't write it as x, if I took the derivative of 7.97 power 1 over 3, I just get a 0, because it's a derivative of a constant. So I had to turn this into an x so that I could find the derivative. So ultimately, this x is my 7.97. And therefore, I know my x has to be 7.97, but I want to keep my a as an integer. So what should happen here? My dx must be a negative 0.03. So if I added a 0.03, I'll get up to an 8. But if I subtracted 0.03, then I come back to my x value. Okay, so that is the idea. So a is 8, dx is negative 0.03, and our x is 7.97. So using this information, and of course the estimation, f of a plus dx is given to be f of x, which is f of a plus dy, of course at x equals a. Right? The function f of x is f of a plus dx, which is given to us by differential estimation formula, that is f of a plus dy. Now let's plug them all in. Okay, so f of 7.97, that's f of 7.97, which is f of 8 plus negative 0.03, which is equal to f of a plus dy was 1 over 3 x power 2 over 3 dx at x equals 8, because x equals a. So I'm rewriting everything here, and here let me write the a as 8. A is 8. So I plug them all in, and I'm going to take it simpler. 3 times, x is 8, right? So the 8 goes in there, times dx. We saw the dx was negative 0.03. I'm going to plug those in there. And let's come back to the function and say f of 8. F of 8 was, f of x was x power 1 over 3, right? I can take you back there quickly. Your f of x is x power 1 over 3. So f of 8 will be 8 power 1 over 3, which is 3. So f of 8 is 8 power 1 over 3. Double one more step slowly. All right, 8 power 1 over 3 is the same as cube root of 8, which is 2, plus 1 over 3 times 8 power 2 over 3. I want you to try and do this without a calculator, at least up to this point, so you understand the way it works behind. 8 power 2 over 3 is the same as cube root of 8 squared, right? Cube root of 8 squared. That's one way to do this. Or you could find the cube root of 8 first and then square the answer. So cube root of 8, because that will be easier here. Cube root of 8 is 2, and that 2 when you square it, because that's the power, 2 squared is 4. So times negative 0 ohms. And that gives us 1.9975. Now, I want you to understand again that this idea was a breakthrough idea, especially at during the age where there was no calculator that computed things for them so quickly. So they had to be a way for them to compute things much simpler. So this might seem complicated to us. Oh, how do I divide 0.03? Actually, it's not so bad, okay? Because 0.03, let me just show that to you quickly before that's going to be 12, right? So that will be minus 0.03 over 12. This is actually a nicer number just because this will be 0.01 over 3 and 12, right? That will be 4. And then when you simplify that, that will give you 0.0025. Which is your 1.9975. So honestly, this is a whole lot easier than computing this entire thing for 7.97. In fact, finding the cube root of 7.97, which is really, really painful. Okay, so it's with that appreciation that I would like you to approach these problems, because you might think, well, I might as well use the calculator and get my 7.97. So we're going to do that too. Okay. So I'll just say the calculator value is for f of 7.97, it's basically 7.97 power 1 over 3. So you can actually do that on your calculator right now. And for power 1 over 3, of course, use the caret symbol. This is called the caret symbol, C-A-R-A-T. If you had the x power y button, of course, use that. But if you didn't have that, look for this caret symbol, and that will raise it to the power. And then you're going to do the 1 over 3 there. And that gives us 1.997496868. If you were to approximate this to 4 decimal places, we got our answer approximated perfectly. In fact, it put up to 4 decimal places, right? If you rounded it at the 4th decimal place, we get the exact answer. So we didn't say, oh, this is very close to 2, so the answer is 2. We didn't do that. We, in fact, came down to 1.9975. And I think that is really, really powerful. It was very important. It was meaningful when these things were discovered centuries ago. And it really helped in engineering also, because they were able to compute using this approximation to a value that was accurate enough for engineering, construction, and for all those amazing monuments that they built at that time when there was really no calculators or computers. So it's really marvelous to see that they had harnessed the idea of differentials to estimate this. I'd like to do another one. So I'll say estimate 1.0002 power 50. How do we do this? Okay. There's a shortcut actually for this. Okay, the shortcut is, if you had, in fact, there's a formula. 1 plus x power k is approximately 1 plus kx. That's really neat, isn't it? So if we were to do that, our k here would be 50. So 1 plus. So separate this 1.0002 as 1 plus 0.0002. Separated it. That's power 50. That would be approximately 1 plus 50 times 0.0003. And that's a whole lot easier to calculate because 5 times 2 is 10. And then look at the number of zeros for the decimal places. So 1, 2, 3, 4. And there was a 0 here, right? So do all those computations if you're doing it by hand. And that comes out to be this, which is 1.01. So the approximate value for this is 1.01. It looks really, really brilliant, right, to come up with that answer. So we can do this if you need a shortcut. If you were to do it elaborately, what we see here is that we have, let me write that one more time here, power 50. So what we see here is that we could rewrite this as 1 plus 0.002 power 50, isn't it? So that means I can rewrite this as I can see this as a dx and this as an a. So this is like your a, and this whole thing is your dx. So a plus dx. Right? So we got that set up. And I want to rewrite this also as a function. So let me write that. So this can be written as x power 50. And I want to call it a y so that when I take the derivative, I can actually use that information. So 50 x power 49, right? One less than that. It'll be dy over dx. And then if I were to write this as a differential, then dy will be 50 x power 49 dx. Okay, all good. Now we need to evaluate this dy. We did all that last time in the formula. I want to just do them separately first. When x equals 1, because a is your it's approximately like your x. So x equals 1 to 50 times 1 power 49 times dx. What was dx? Dx was 0.0002. What's really neat is anything power, 1 power anything, sorry. 1 power anything is coming back, it's going to come back as 1. So that's going to be 50 times 0.0002, which is 0.01. Okay, so dy when x equals 1 is that. I want to put all of these together. So we know that f of x is the same as f of a plus dx, which is basically f of a plus dy at x equals a, isn't it? So let's rewrite all of these things for our given problem. Okay. So we have f of x one point 0002, which was f of 1 plus 0.0002, which is f of a, in this case a is 1, f of 1, plus dy when x equals 1. So we found f of 1, and then we can just compute that here. Okay. Now f of x is x power 50, so f of 1 will be 1 power 50 plus, we just found dy at x equals 1 to be 0.01. So 1 power 50 will come back as 1. So 1 plus 0.01, which is 1.01. We get the same answer when we do the elaborate way, right? 1.01, which is what we got when we did the shortcut by seeing it as 1 plus x the whole power k. Again, there are several shortcuts like these that you may come across if you did a little more research that can come in handy. But whether you know the shortcut or not, this elaborate method, which is the estimation method, will always come in handy. It will always work for us, even if you didn't have any nice handy shortcuts like this. We'll do one more, and this time we'll use the shortcut. Okay. Estimate cube root of 1.009. So what we can do now is rewrite this cube root of 1.009 as 1.009 the whole power 1 over 3, isn't it? Which can be rewritten as 1 plus 0.009 power 1 over 3. I'm separating the 1 and the decimal part. And we know that from that trick or that shortcut, this is approximately the same as 1 plus this 1/3 times 0.009. And that is going to be, the 3 and the 9 will cancel each other, right? So that's going to be 0.003 and 1.003. If you're curious, you can pull out your calculator and compute it to compute cube root of 1.009 and see if that gives us this answer. All right, let's wind up with this last problem. Use the differential dV to estimate the change in volume of a sphere when the radius changes from 9 to 8.8. Round your answer to the nearest tenth if necessary. Recall that the volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. V is equal to 4 over 3 pi r cubed. And we're supposed to find dV, right? And obviously it says dV to estimate the change in volume when the radius changes. So dV over dr is basically what we're trying to find, because we're trying to find the derivative with respect to r, the radius. And so that will be 4 over 3 pi. All of these are constants, so keep them together, times 3r squared, because we're taking with respect to. So I'll just say differentiating with respect to r. And that information comes right from here. Change in volume when the radius changes. Okay. And they want us to find dV. Therefore, dV will be, simplifies here, 3. dV is 4 pi r squared dr. So in our question, they're saying the radius changed from 9 to 8.8. Radius changes from 9 to 8.8. It went through a small change. So what this really means is that your r is 9 and the change was the dx. So from 9 it went down to 8.8. So it went down by 0.2, isn't it? So that's a minus 0.2. It went down. So all you have to do is plug them in your dV expression. So I have 4 pi and r is 9 squared and dx is negative 0.2. So this approximately is negative 203.6. So we have approximated the dV, the change, right? The change in the volume. And so if you were to interpret this, we'll say we estimate. This is estimation, you know that, right? Because that formula that we're using by plugging in for r as 9 and dx as this comes from the formula which we use to estimate differentials. So we estimate that the volume of the sphere note that you have a negative volume, right? So that means it decreases by 203.6. Remember, this is volume, so it has to be in cubic units. We don't know what the unit was. They didn't say centimeters or inches or whatever. So we'll just say cubic units when the radius decreases. from 9 to 8.8. It's all lining up nicely. And again, remember the units for the volume, and make sure that you indicate the minus by the word decreases. Okay. So this was another example, a real life example of how we could use the differentials to estimate it. With that, we finish off with this section in chapter 4. I will see you in the next lecture.